Okay, example number 1 from lesson 4. It says, given f of x equals 1/3 x cubed minus x, determine the open intervals on which the graph is concave up or down and state the point of inflection and explain how you know. So the first thing we're going to do is we're going to find f prime of x. So this should give us x squared minus 1. Now remember, if we took this derivative, we're just going to do this over to the side and we set it equal to 0. And I guess you could move that 1 over, you could factor it. If you take the square root of both sides, you have to remember plus or minus. These would be your critical points for your first derivative, right? So I'm going to put critical points for first deriv. That, if you made your sign chart, you know, -1, +1, and looked at your f prime on either side, so you'd be putting like a -2 in, squaring it, you get +4 minus 1, that would give you a positive value. Put 0 in, that would give you a negative value. Put +2 in, that would give you a positive value. And our first derivative test, if it goes from plus to minus, then we have a max, and if it goes from minus to plus, we have a min. We don't really need to do that here, because they're only asking for upward, concave up and concave down. So we're going to go straight to the second derivative, which is just 2x. And to find the critical points for that, we're going to look for where it's 0 or undefined. So divide by 2, and the critical point for the second derivative is x equals 0. So now we're going to take that and make a sign chart, and we're going to be looking at what f double prime is doing. If I have a -1 that I put into this second derivative, I'd get -2, so I'd have a negative value. If I put +1 in, I get a positive value. So now think about what the sign chart for the second derivative is telling us, okay? In our definition, if the second derivative is negative, then you have concave down. If the second derivative is positive, you have concave up. So we can say, so here's our third thing. We're going to actually answer our questions. We're going to say f of x is concave down from -infinity to 0, and because f double prime of x is less than 0 there. F of x is concave up from 0 to infinity because f double prime of x is greater than 0 on that interval. Okay, so there are our concavity intervals based on the sign chart and the critical point of the second derivative. Then it says state the point of inflection and explain how you know. Well, by definition, if your second derivative changes signs, that means it goes from negative to positive or positive to negative, then that critical point is considered a point of inflection. So since this second derivative goes from negative to positive, we know that we have a point of inflection where x is 0. So to find out what your f of 0 is, so we can actually make it a point, we're going to go back to our original function up here, and we're going to put 0 in for x, and we see that we get 0. So now we can say there is a point of, or how about, well, I'll go ahead and write it like that. There is a point of inflection on f of x. Now, notice that I've been including, f of x in here, because remember, we're using the first and second derivative to tell us things about the original function. So the second derivative, because we found the critical point and because we found where it was negative and where it was positive, it was telling us where the original function has that concavity and where the original function has the point of inflection. So we want to make sure we state that. So there is a point of inflection on f of x at 0, 0 because and I'm not going to say sorry, because f double prime of x goes from negative to positive at x equals 0. Okay, so we're saying that, hey, we know that there's a point of inflection because the second derivative is changing signs at that x equals 0. And so I found out what the y value was by going back to my original function. So that is exactly how you would write it on the AP exam, and of course what I'm going to be looking for. Do you see how, for what it was asking, we really didn't need this at all, but I wanted to connect it to what we had just done in 5.3. So now let's look at example number 2, the concavity, which you would find by the second derivative, and the direction of the function, which you would find by the first derivative, is related to the slope. Okay, so they want you to graph f of x and graph f prime of x. And so what I did here is I just made a little chart. And since I knew up here that my critical points were -1 and +1, and that I had a maximum at negative or at +1, and I have a minimum at I have a maximum at -1 and a minimum at +1. I'm looking right here to get that. I'm going to choose, and I also have the point of inflection at 0. I'm going to choose -1, 0, and 1 as my x values that I'm going to try and find points, because I know that at -1 I've got a max, and at +1 I got a min, and at 0 I have a point of inflection. So if I put -1 in, I get 2/3. If I put 0 in, I get 0. If I put 1 in, I get -2/3. So I just, graphed like, approximate points here. But I knew that this was a maximum, and I knew I had a, sorry. I knew I had a minimum, a point of inflection at 0, 0, and a minimum, I cannot see, at x equals 1. And I know what a cubic function looks like, okay? So I had an idea of what this cubic function was going to look like. So there's the that one, and then this one's just, a translated version of x squared. So there's that one. Now, and what we said here, well, we didn't say it, but this is where our, this point and this point was where our derivative was 0. So that makes sense. Remember, we up here when I set that derivative equal to 0, and it gave me -1 and +1, here's my derivative function, and here's where my derivative is 0, and it makes sense. So if I was doing a sign chart, looking at the derivative, I'd be like, oh, okay, well, I can see it's positive. Then it goes below the x-axis, negative in between -1 and 1, and then it goes positive again. So you can actually look at the derivative function and see when it's above the x-axis, when it's below the x-axis for these. And remember that the positive ones were telling me where your original function was increasing. So where f of x was increasing. So I could have done increasing and decreasing intervals from this. -∞ to -1, it was increasing, and also from 1 to infinity, and decreasing intervals. So this is telling me that it's decreasing, that f of x is decreasing. So decreasing from -1 to 1. So this is where this function is increasing or decreasing, okay? And we're looking at the derivative to figure that out. So in summary, we had critical points at -1 and 1, and that was where our derivative was 0, and our derivative went positive, negative, positive, and we knew that this was my max, this was my min, and we knew increasing, decreasing, increasing based on that sign chart of my first derivative. My second derivative, the critical point was 0, and we knew that this was negative and it was positive, and that told me that this that the original function f of x was concave down on from negative infinity to 0 and concave up from 0 to infinity. So now, when you're looking at that on the original function, is it telling you the truth? Is it concave down negative infinity to negative, or negative infinity to 0? Concave down negative infinity to 0. Yes, it is. Then point of inflection, then you've got concave up from 0 to infinity. Okay, so that does make sense. That's what it's doing. It also, the first derivative told me there was a maximum here. It wasn't an absolute max, it was a relative max, and a minimum here. It wasn't an absolute min, it was a relative min. And we knew that before we even started because cubic functions will have only the relative. They will not have absolute. So hopefully that example kind of gave you everything kind of in a nutshell. We were able to connect increasing and decreasing, first derivative test, and now our new stuff about the second derivative and concavity intervals and points of inflection, and bring that all together so that we can see it together. So definition for point of inflection, let f be a function that is continuous on an open interval and let c be a point in the interval. If the graph of f has a tangent line at this point, c comma f of c, then this point is a point of inflection of the graph of f if the concavity of f changes from upward to downward or downward to upward at the point. So if c comma f of c is a point of inflection of the graph of f, then either the second derivative is 0 or the second derivative is undefined. And that is kind of what we talked about here. So you can see that about right here on this function is where concavity changes. So you can see that you've got concave up here, and then it goes to concave down. And so right where that changes, if we follow that down, that point P, that would be considered that x equals P is your point of inflection. And so you would look at, here's the equation of the tangent line, and you can see that your, at P, that your derivative is greater than 0, and that your second derivative at P would have been 0 because it's changing concavity there. That would be your critical point for your second derivative. For this one, I see concavity changing about right here. Put it in black. And so if I follow this one down, this is my x equals P. And I can see I have concave down on this side. I have concave up on this side. It's like cupped up. But look, that is a brief little second derivative of 0, right? But so your first derivative, sorry. Your first derivative is 0, right? Because that's the slope of your tangent line. But your second derivative would be 0 at that point also. Sorry. So now, next one, I'm going to do this one in blue. It looks like it's changing concavity about right here. It might not be exact, but I'm going to follow that down. That's my x equals P. And so you can see right here I have concave up. And here I have concave down. And if I looked at my slope of my tangent line here, I think it would actually be vertical. It looks like a vertical tangent right there, although it's hard to draw. And so that would mean that my first derivative would be undefined because it would be a vertical tangent, okay? My second derivative would be undefined there also, but it would still be a point of inflection where your concavity changes. Okay, so all of these are, this was no extrema here. Remember when you've got your f prime of p equals 0, but sometimes you have an extrema and sometimes you don't, because your slopes of your tangent lines were positive, 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 went to 0, but then they were positive, positive, positive again. So on your first derivative, when you had p here, you went from positive to positive. So there was no extrema there. Here, there was also no extrema. I'm going to do a different color. This one was no extrema also. Positive, 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 right? But you had an undefined term at p, and it went from positive to positive for your f prime. And so no extrema, but still you ended up, since your second derivatives was also a critical point at p, and it went from positive to negative because it was concave up to concave down, it ended up being a point of inflection where your concavity changed, even though it was not an extrema. Okay? So just the different things. This one wasn't an extrema, so we didn't have to worry about it because your first derivative was, greater than 0. So that one, you didn't even have to worry about it. But when you have 0 for your first derivative or undefined for your first derivative, then you're, really thinking about, okay, well, is that an extrema? And it isn't for those. Okay, I know this is a lot of stuff, so just bear with me because there's a lot of different situations. So let's explore the possibility that a graph could change concavity at a discontinuity. Say a vertical tangent line, or where f double prime doesn't exist, such as at a cusp. In the case of a vertical tangent line where the x value is not in the domain of the function, then the value x equals p will not be an inflection point. So here are a few examples. So for this one, your second derivative at p is 0, okay? And you can see it changes concavity. Here, your second derivative at p does not exist, okay? Your first derivative does not exist, but it ends up being an extrema. Your second derivative does not exist, but when you do your sign, look, it goes from being concave up to concave down. So it still is an inflection point. So these two, you still have inflection points for that situation. But over here, look at what happens. So your first derivative does not exist, right? Oh, I put x instead of p. Your second derivative at p does not exist. Okay, and is it an inflection point? Well, it goes from being concave up and then it goes to concave up again. So on your second derivative, you would go from plus to plus. So that would be no inflection point. And then this one, your first derivative at p does not exist. Your second derivative at p does not exist. P is not even in the domain of your function. So, so even though it goes from being concave up to concave down here, it would not be considered a point of inflection because it's not even a point. It is a vertical asymptote. So your concavity changes, but it's not at a point, okay? All right, so now some important thoughts. We will use a second derivative sign chart to determine intervals of concavity as well as actual inflection points. The possible points of inflection can be called critical values of f prime of x. Remember, concavity can change at a discontinuity, such as a vertical asymptote, but it won't be an actual inflection point. In order to classify an x value as an inflection point of a function f of x, the x value must be in the domain of f of x. So even though concavity changes on a problem like this, on a situation like this, you do not have an inflection point at p because p is not in the domain of the function. So example number 3, determine any points of inflection and discuss concavity of the graph of f of x equals x to the fourth minus 4x cubed. Okay, so the first thing we're going to do is find our derivative. And so we're going to say that this is 4x cubed minus 12x squared. I wanted to set it equal to 0, and at the same time I was going to factor out what was common, and 4x squared was common, and I'm left with x minus 3. So if I set that equal to 0, that gives me x equals 0. Set that equal to 0 gives me x equals 3. And so those are your critical points for the first derivative. Our second derivative would be 12x squared minus 24x. I set that equal to 0. I see that 12x is common to both. I'm left with x minus 2. Set that equal to 0. I got x equals 0. Set that equal to 0. I got x equals 2. And these are your critical points for your second derivative. So, and since they're asking about points of inflection and concavity, we're going to put our 0 and 2 here, and we're going to be looking at f double prime sign. So, if I tested, like, let's say -1 here, let's say I'm going to test +1 here and test 3 here. Those are, just you're picking one point to the left of 0. And looking at what the sign of f double prime would be. So if I put that in, I would get a negative times a negative, which would give me the sign for f double prime as positive. If I put a 1 in, I would get a positive times a negative. That would give me a negative for in between 0 and 2. And if I put a 3 in, I would get a positive times a positive, which would give me a positive for my f double prime. For the interval from 2 to infinity. So now we have to decide, is x equals 0 a point of inflection? Like, is there a point of inflection at x equals 0? It changes from positive to negative. So yes. Here at x equals 2, it changes from negative to positive. So yes. Okay, so first we're going to say there is a point of inflection on f of x at 0, comma blank and 2, comma blank. Okay, so I'm going to go back to my original function. If I put a 0 in, I get 0. Back to my original function, that will give me 16 minus 32. So that'll be negative 16. And we could say because f double prime of x changes from positive to negative at x equals 0, and f double prime of x changes from negative to positive at x equals 2. Okay, so that takes care of your points of inflection. Now we have to take care of our concavity intervals. So let's say f of x is concave up on negative infinity to 0, union 2 to infinity because f double prime of x is greater than 0. And then we could say that f of x is concave down on 0 to 2 because f double prime of x is less than 0. Okay, so that is giving your concavity intervals based on your sign chart for your second derivative and giving the reason why. That would be your justification. So when it says justify, that would be your justification. And this one says discuss, so that means basically talk about it, say why. Okay, example number 4, find the inflection point and the open intervals of concavity. Justify, and it's given g of x equals 1/2 x plus sine of x on 0, 2 pi. All right, so now, first thing that we do, take our derivative. 1/2 plus cosine x. I'm going to go ahead and set this equal. So we would be looking for, if we were looking at critical points for this, because a lot of times, even though this lesson is specifically on the second derivative stuff, but once we get past learning this, it's going to ask you several things. And so I'm just going to go ahead and, do a little bit of this. So this is your critical, or no, I got to find your critical points. We want to look to see where cosine is negative. All students take calculus. Cosine is negative in the second and third quadrants. So -1 over 2, -1 over 2. So this is going to be a positive square root of 3. This is going to be a negative square root of 3. So this is a 60 degree or pi over 3 angle, but this is happening at 2 pi over 3. So x equals 2 pi over 3, and then 3 pi over 3, 4 pi over 3. Because my 3 pi over 3 was here at pi, and then 4 pi over 3 was one more. Those would be your critical points for your first derivative, okay? And then we would find our g double prime of x, which would just be negative sine x. And when we set that equal to 0, again, we'd just be looking for where, if I divided by -1, we're looking for where the sign is 0. And so between 0 and 2 pi, our sign is 0 at 0, pi, and 2 pi. Okay, so those would be your, and 0 and 2 pi are your endpoints also. All right, so now, those are the two things that that we would do when we were given a function and we want to talk about points of inflection and concavity and all that stuff. So first thing that we're going to look at is our sign chart for our, because they want us to give points of inflection. So let's make a sign chart. We've got our 0, we've got our pi, we've got our 2 pi. We're going to be looking at g double prime. I'm going to go ahead and pick a point in between to test. I'm going to pick pi over 2 to test, and I'm going to pick 3 pi over 2 to test. And so if I, and remember, here's your g double prime. It's negative sine x. So if I put negative sine of pi over 2, that sine of pi over 2 is 1. That's going to give me -1, so that gives me negative. If I put in sine of 3 pi over 2, it's -1 times a negative is a positive. So for my derivative, I'm going to have my, between 0 and pi is going to be negative, between pi and 2 pi is going to be positive. So now you can see that at pi, you have, you're going to have a point of inflection. So you're going to say g of x has a point of inflection at pi, comma. Now, if I go back up to my original and I tried to find out what g of pi was, it would be 1/2 times pi plus the sine of pi. And so that's going to be pi over 2 because the sine of pi is 0. So this would be at pi comma pi over 2 because g double prime of x changes from negative to positive at x equals pi. Okay, so that's the first thing that they wanted us to talk about. Second thing were our concavity intervals. So second thing I'm going to say is that g of x is concave up on the interval from pi to 2 pi because g double prime of x is greater than 0. And then lastly, g of x is concave down on 0 to pi because g double prime of x is less than 0. Okay, I'm going to stop.